Okay, let's talk about light today. Okay, so we'll be talking about light in terms of polarization. Okay, so we know that light here, our main focus of light will be as wave. Okay, now wave nature, we'll focus on wave nature of light. Now, what light is actually, it's combination of two kinds of waves or two fields. Okay, it's a combination of electric field. Okay, pardon my drawing if it's not that accurate. So it's a combination of electric field and magnetic field. So these in combination make up the light in terms of wave. So what polarization, here our topic is polarization actually. Polarization. Okay, now what polarization is that we by the way, this full wave over here is known as unpolarized light, because here if I draw this, it would be incomplete. Okay, it would be complete wave. How it's incomplete wave is, I'll show you it. So here, when light from the sun reaches our eyes, okay, when it reaches our eyes, this is the correct way I would draw this wave is, or this light is. If I zoom into this light in terms of theory, of course, so it doesn't only have vertical and horizontal orientation, but it has orientation in this direction, it has orientation in this direction as well. So it's in all directions, not only one direction. Okay, so this is what unpolarized light is. This is light, this is unpolarized light, in which the orientations or the oscillations of the light is in all directions. Now, the the topic polarization means that we pass it through a certain sheet. That's right shape, of course. That's right shape, by the way. So the sheet is known as polarizer, no wonder, or it's also known as polar polar polarized sheet. Okay, polarized sheet. So what this sheet does is, it has like certain directions made on it. Okay, and when light passes through this polarizer, okay, the light passed through this, it's in this is how light will look like as it passes. Okay, it has both horizontal and vertical orientation, but the moment it will go out of this polarizer beat on this side, what we will see is that since it's a vertical polarizer, it's a vertical polarizer, what we will actually see is that in after it has passed through this polarizer, we will only have vertical part of the light. The horizontal part was stopped. Now here's why. Because now what polarizer does is, it will only let the same orientation as that polarizer light go through, and not the one which is perpendicular or which is in other directions. So now we have, first of all, we had electric and magnetic. Now we have electric only wave. Okay, or we have half the polarized wave. Now what here if we have another polarizer, and that polarizer now has uh, horizontal horizontal orientation. Okay, now this light goes through. Now what we see in the end is not too bright, too bright light. Okay, or in layman words we say there's no light, no light. Okay, okay, but even though there will be some light, of course. Now here we just made light polarized from this to this, and from here it became nothing. Now then, no, wait, it went only. So no light, yeah. Horizontal polarization means vertical part will be stopped. Yeah. So yeah. So what we did is that now here's the use of polarization. Now imagine we have uh like a lake. Okay, we have a lake. It's a practical application of light, of water, of polarization, and this is one way we can also polarize light. Now imagine we have this is a lake and we have fish in this. Okay, ignore my fish. Now when if I'm standing here, okay, if I'm standing here, wait, sorry, if I'm standing here and I'm watching this fish. Now it would be very hard for me to see fish if there's too much light, right? Now, okay, I have it. It wouldn't be very easy for me to see light or this fish. Now, if I have a polarizer, or if wait, you can do polarization in this as well through this is known as polarization, sorry, polarization through reflection and refraction, which are two topics of optics, which in which this polarization also comes in. Now what we actually see is when light, it's better to use this color, is coming in, or wait, let me make it better, this, this, this. Now look at this, it has two orientations, one is in horizontal and one is vertical. Horizontal, vertical, horizontal, vertical. But after it has hit this water surface, you will observe is that horizontal, or one of the orientation of light went in water, and other one which is other orientation went in reflected back, reflected back. Now look, we went from unpolarized light to polarized light. Is that cool? That is cool. So what does that mean for us? So if, let's suppose, if we wear sunglasses, so when we wear sunglasses, actually we're talking about it's just still the same topic, okay? Now when we wear sunglasses, okay, technically what we do is that we are able to see the fishes, right? If we're in a sunny day and it's too much like sunlight, so we can't see inside the water clearly, like because of the reflection of the light from the sun to the sun water surface to our eyes. So what we are able to see the fish. Now, how are we able to see the fish is thanks to light polarization. Okay. Now, what do I mean by light polarization is in our sunglasses there are polarizers, okay, and I won't go. I'm not sure about like if the polarizers are like same in both. If like it should be same, of course. So what the polarizers do is it stops the reflected light, okay, also does glare, okay. Glare of the light means the reflection we see of the sunlight from the water surface is moved on. We don't see that anymore. What we see is the light which is inside the water. Inside the what we see is inside water light. Inside water light. Okay. So this is look. So what happens is inside water light seen only, okay. This is the reason we have better vision of our surroundings in daylight using sunglasses. And I think, by the way, you guys know about this these glasses which have the special property that when when light is shine or should I think on it, it 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 changes, okay. Now what do I mean by it changes? I mean like let's suppose if they have nothing in the nice glasses I made, impressive. They're not red, of course. Now this is all white, okay. By white I mean normal sunglasses, like normal glasses. But the moment they go to sunlight, when they see sunlight or the rays are coming in, what actually happens is this glasses, the color changes to black, okay. Now what actually happened is they have some kind of polarizers in them which react to the sunlight, okay. Polarizers which only react when they detect a large huge amount of sunlight and they turn black. So they are again they are reactable polarizers. That's why in my mind it's a reactable polarizers, meaning when they see light or uh, when they see what do I say when they see or when they have when they shed too much light more than the maybe required range they have inside them, they turn into black or like the range which is not good for our eyes. So that's why now to think to be think to like to think of it, when we look straight into the, when we look, like, let's put the person over here, okay, and what he does is he looks straight into the sunlight, okay. Now we know that sunlight is, as if we look at straight into it, it's unpolarized. It's, what is it? It's unpolarized, unpolarized, unpolarized. Okay, so it's very dangerous because it has all kinds of orientation, all kind of direction in that plane. So it does hurt, right? It gives pain. And one more thing is that its medical health issue is that it can make people go blind. That's one of the and it can give any other health issues as well. That's why we are advised not to see straight into the sunlight because of the multiple orientations or light being unpolarized is the condition. When you wear sunlight sunglasses, you have polarizers in your sunglasses. They will only give you the sufficient amount of sunlight, which will make your vision uh, accessible for that area without damaging your eye. But without glasses, or without glasses, sorry, without glasses, you should never look straight into your eyes, into the sun. It gives a huge headache, it gives pain, and there's a lot of health issues inside it. So it's better not to look straight into the sunlight without any protection or without any protective glasses. So, but here, now let's talk about one last phenomena of light, one last topic of light, which will which changes our way of, which will here, because which will make us go from quantum mechanics to, oh, sorry, classical physics to quantum mechanics. Classical physics, or wait, classical physics to quantum mechanics. Okay. Now, what is that simple topic, and why is it? And by the way, it's very like special. It's like it shows the weirdness of light. And first of all, to even begin with, even though it should have been said at the like start of the episode, or start of the video, is that light is not as simple as we think of it. It's very mysterious, and here's why. Pardon. Now, what I will be doing is that I will be doing the same experiment which I would do over here. Okay. Now, what's so special about the experiment I will do here is, the special thing about this experiment is that we will be doing polarization, okay, of light, but we will add one more polarizer. Okay. Now, what is this one more polarizer? What's so special about adding this one more polarizer? Now, let's see. Now, again, let me set up the experiment. We have vertical orientation. We have a horizontal orientation. Now, what's a degree? They are 90 degree angle, right? 90 degree. Like, actually, this is 0 degree. This is 90 degree. Now, what is so special about this one? is that as we add a third polarizer, the property of this third polarizer is that it has a 45-degree turn. Here we have a degree difference of 45. Now, what's so special about this adding this third polarizer which changes or which shows the weird behavior of light? Now, here we go. Let's start this small session on the weirdness of light. For now, let me just say this is light, okay? Light is coming from here. Now, we know that when light passes the vertical polarizer, we have on this part vertical 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 field, which is electric field of light, as horizontal was stopped. Now, after this, everything changes. Okay. Now, first of all, let me write something over here. Here we had R here. What is the state of light? Vertical, right? Now, what I mean by state of light? Now, light is actually, there's one phenomena of light that one of the phenomena of like phenomena of quantum mechanics in particular is that when we do a certain measurement, and here these polarizers act as measurements. Okay. Now, what this polarizer did is change the current state of light to another state. According to that, according to quantum mechanics, the light is now in that state until another measurement is made. Now, now this is our true state or current state. So now here's the magic or the weirdness of light begins. The moment it passes through the diagonal, this is a diagonal polarizer. Diagonal polarizer, magic. What we see is light has turned from vertical back into vertical and horizontal polarization, like a horizontal wave. Here we go. How is that possible? Now that is what all scientists till now are trying to see. Why does light behave like that? Why does quantum mechanics behave like that? So now the fun fact is that before, when we were over here talking about this part, we had dim light or no light in particular, or like in simple words, changes the fact that here now we have 50-50 chances. 50-50 chances that we will have more amount of light here. More light in the end. Now, by the way, if I make a polarization, this is perpendicular. This is the vertical polarization. This is the horizontal polarization. Can't I say that this polarization over here, this one over here, is superposition of both, superposition of both the electric and magnetic field. By the way, these symbols present electric and magnetic field. Okay, can I say that? Yeah, I can, because this here is nothing but a superposition. That now, before we had only vertical and vertical orientation after it passed from the first polarizer. Now we have, after passing diagonally, it had superposition of both, which made us have more light in the end as compared to the light we had in the we had in the this part of the polarization, the when we only had vertical and horizontal. Now, so this is why we have now 50-50 chances, okay, that either some of the light will go through and some of the light will stop. This chance over here gives us, that's the weird behavior of light. That why does taking this, only this adding one more additional polarizer, which is a horizontal or diagonal polarizer, change the way light behaves. Now again, to give a summary of this whole small thing, is that after the horizontal, after the vertical, the light turned into a vertical field, a vertical vector. Now after the vertical vector it passed through a horizontal, instead of not like something else happening, or we don't know what would have happened if this didn't happen. What we saw is that light turned into a superposition of both horizontal and vertical, and that superposition caused the end result after it passed through horizontal to have either 50-50 chance of us having light and no light. Now since we will have more light now, so you can say that this diagonal polarizer is a savior, right? It saved that small amount of light for us to have more light, or we having to have a bright spot or bright point at the end as compared to this one. So here what I think is that even though at this point half the light was vanished, this diagonal turned that same light into 100% again, and that 100% got into half the light again. Half of the light was small, so that means we are looking at, so what we are looking at is half half missing light. Okay, that's what we see at the end. Like, in my opinion, of course we have different opinions. So this is here, certain amount of light was stopped here. That same amount of light turned into superposition of both horizontal and vertical as measurement was made. Again, measurement was made here, measurement was made here, measurement was made here. Every change in quantum mechanics is nothing but measurement being done, and that measurement being done is nothing but the collapse of wave function. What I mean by collapse of wave function is that wave function did not, over here the light had this wave function, but here it changed into another wave function, and then there it had another wave function, giving us result of wave function being broken. The simple term wave function is nothing but shows the multiple states a particle or and particle in quantum mechanics can be until it is collapsed. When it's collapsed, it turns into a definite state, a definite area. Wave function. Okay, is the probabilistic nature of particle, or way of, not nature, way of showing particle in multiple states until a measurement, or that here in terms of polarization, measurement is the polarizer is made. Okay, that's what, and this is the symbol for wave function. And yeah, this is how it looks like. Here, here, higher probability, and here lower probability. Okay, that's it. Thank you.